Welcome everyone. Today we are going to explore one of the most important finite difference schemes in computational fluid dynamics, the BTCS scheme. BTCS stands for backward in time centered in space. This is an implicit scheme and it's the foundation for many solvers that handle diffusion problems and with extensions. It even appears in algorithms for the Navier-Stokes equations. We will start with the simplest possible model, the one-dimensional heat equation, and then we will build up to nonlinear systems, stability analysis, and efficient solution techniques. So by the end, you will understand not only how BTCS works, but also why it's so widely used and what its limitations are. Now, let us begin with the equation that governs heat equation in a rod. The one-dimensional heat equation, which can be represented as partial u or partial of t equals to alpha second derivative of u with respect to x. Now, u is a function of x and t. It actually represents the temperature at position x and time t. The parameter alpha is the thermal diffusivity, a measure of how quickly heat spreads through the material. We will consider a rod of length L with some initial temperature distribution, and we want to know how that temperature evolves over time. So the physical interpretation is very simple. The rate of change of temperature at a point is proportional to the curvature of the temperature profile at that point. If the profile is curved upward, the temperature will increase. If it's curved downward, it will decrease. So to solve this equation numerically, we have to discretize both space and time. We introduce a grid as x subscript I equals to I times delta of x for I ranging values from 0 up till n, and I raised to the power n equals to n times delta t for n values 0, 1 up till so on. Now, the unknown temperature at grid point xi and the time level I raised to the power n is denoted combinedly as ui raised to the power n. Now, the key decision is how to approximate the derivatives. The BTCS backward in time centered in space scheme chooses to evaluate the spatial derivative, the second derivative with respect to x at the new time level n plus 1. That's what backward in time means actually. We use the future time level for the spatial term. Now the time derivative is approximated by a simple forward difference between the new and the old time levels. So we write this particular equation as displayed. In this equation, the right hand side is the standard central difference for the second derivative. But notice all the u's are at the time level n plus 1. So that's the centered in space part. So at each time step, we have an equation that relates the unknown values at the new time level to the known values at the old time level. This is fundamentally different from the explicit schemes like FTCS, forward in time centered in space, which we have already discussed previously, where the spatial derivative is evaluated at the old time level. In explicit schemes, you can simply march forward in the time. In implicit schemes, however, you have to solve a system of equations at each time step. That added complexity comes with a huge benefit, unconditional stability, as we will see soon. Now, let us rearrange the equation to isolate the unknowns on the left-hand side, multiply both sides by the delta t, and bringing all terms containing u at the new time level n plus 1 to the left. So where we have defined the lambda equals to alpha delta t over delta of x whole square. So this lambda is often called as a diffusion number. Now expand the parentheses and combining the terms that multiply ui at the time level n plus 1. So we get the final relationship as displayed over this particular slide. So this is a nonlinear equation actually that connects the three unknowns at the new time level. Now the value at the current grid point and its left and right neighbors for every interior point I equals to 1 to up till n minus 1, we have such an equation. Now, to complete the system, we need to specify the boundary conditions. Let us assume the Dirichlet boundary condition, which states that the temperature at the ends of the rod is already prescribed, say U naught at time t equals to GL at time t, and UN at time t equals to GR at time t at time level n plus 1. These values are known from the boundary conditions. So for the first interior point I is equal to 1, the equation involves u naught at time level n plus 1, which is known. So we move that term to the right hand side. Similarly, for I is equal to n minus 1, uh, un raised to the power n plus 1 is known. For the boundaries themselves, we don't need to solve for them, so they are given. If we write the system in the matrix form, it becomes u n plus 1 equals to u n plus b. Here u raised to the power n plus 1 is a vector of unknown interior temperatures or all grid points if we include the boundaries as trivial equations. A, however, is a tridiagonal matrix. Each row has entries minus lambda on the subdiagonal, whereas 1 plus 2 lambda on the main diagonal and minus lambda on the super diagonal. So the vector B comes from the boundary conditions. So let us take a moment to appreciate the structure. For a grid with say 5 interior points, the matrix would look like this as displayed. Notice that it's sparse. Almost all entries are zero except on the three diagonals. This is a huge advantage. Solving a tridiagonal system can be done very efficiently with the Thomas algorithm, which is a specialized form of Gaussian elimination that runs in O n operations, not O n raised to the power cube operations. So this makes BTCS, backward in time and centered in space, very practical even for very fine grids. So the key takeaway over here is that by using an implicit scheme, we have turned a time marching problem into a linear algebra problem at each time step. The extra work is worth it because we can now take much larger time steps without worrying about the stability. Now, before we dive into the math, let us build some intuition in an explicit scheme like forward in time centered in space, which we have already discussed. The stability condition was lambda must be less than equal to half in value. That means if you double the grid resolution, making delta x half as large, you have to make delta t 4 times smaller to keep lambda constant. So that's a severe restriction, especially for long time simulations. Implicit schemes like backward in time centered in space removes that restriction. Why? Because at each time step, the information from the entire domain is coupled together through the matrix solve. Essentially, the influence of any point spreads instantly to all other points in one time step. This coupling makes the scheme unconditionally stable. There is no time step in limitation for stability, though as we will see, accuracy still imposes limits. To prove the unconditional stability, we use the von Neumann analysis. The idea is to examine the behavior of a single Fourier mode. We assume the solution can be written as a sum of modes of the form as displayed over here of the term ui raised to the power n, where k over here is the wave number and I here is the imaginary unit. We substitute this into the BTCS equation. First, we compute the spatial second derivative, and then as we know that from the trigonometry identities, e raised to the power I k delta x plus e minus I k delta of x equals to 2 cos of k delta of x. So the term becomes as displayed, and when we plug this into the discretized equation and cancel the common factor, and so we can define the final amplification factor as g plus 4 lambda sine square k delta of x divided by 2 times g minus equals to 1, which would be giving us the final form as g equals to 1 over 1 plus 4 lambda sine square k delta of x divided by 2. Now examine this particular expression since lambda is greater than 0 and the sine squared is between 0 and 1, the denominator is always greater than or equal to 1. Therefore, the amplification factor in the range less than equal to 1 and greater than 0 for all the wave numbers k and for any lambda. That means the magnitude of the amplification factor is always less than or equal to 1. In other words, every Fourier mode is damped or at most stays the same. There is no growth. This is the mathematical proof that backward in time centered in space scheme is unconditionally stable for the linear diffusion equation. Now we must be very careful. Unconditional stability does not mean unconditional accuracy. The truncation error of the backward in time centered in space scheme is first order in time and second order in space. So if we take a very large time step, the temporal error can become huge and the solution may lose physical meaning. For example, if we try to simulate a rapidly changing temperature field with a time step that is too large, the implicit solver will still produce a stable solution, but it will be smeared out and inaccurate. In practice, you choose the time step based on the smallest time scale you need to resolve. For diffusion problems, that often means lambda is on the order of 1 or less, even though the scheme remains stable for much larger values. So the trade-off is that the stability is granted, but accuracy still dictates a reasonable time step. Now, let us talk about how we would actually implement backward in time centered in space scheme. We will walk through these steps without writing the actual code or in the software, just describing the algorithm. First, we define the physical parameters, the length of the rod, the total simulation time, the thermal diffusivity, the number of the grid points, and the time step. We also compute the grid spacing and the diffusion number lambda, and we set up the initial conditions for each grid point. We assign the temperature at time 0. Next, we would be building the coefficient matrix because the matrix is tridiagonal and constant for constant alpha and uniform grid. We can pre-compute the main diagonal entries 1 plus 2 lambda and off diagonals minus lambda. We also incorporate the boundary conditions. For Dirichlet boundaries, we modify the first and the last rows of the matrix so that the solution or at the boundaries is fixed. This is done by setting the diagonal entry to 1 and the off diagonals to 0 on those rows and adjusting the right hand side accordingly. Then we enter the time loop at each time step. We form the right hand side vector for interior points. It's simply the previous time step solution. For boundary rows, we set the right hand side to the prescribed boundary values. We then solve the linear system. For a tridiagonal system, we use the Thomas algorithm, a direct fast solver, and the solution gives us the temperatures at all grid points at the new time level. Finally, we update the solution and proceed to the next time step, and at the end we can visualize the results. Now, if we run this for a simple test case, say a sine wave initial temperature distribution with zero temperature at the end, so we observe that the sine wave decays smoothly over time as expected from the analytical solution. Now, let us test the stability claim. Suppose we set delta t to be very large such that lambda equals to 100. In an explicit scheme, that would cause an immediate blow up, but in backward in time centered in space, the code runs without any blow up. The solution remains bounded, but if we compare it to the true solution, we see that the decay is much too slow. In fact, the solution may almost look frozen because the time step is too large to capture the physical dynamics. This illustrates the difference between stability and accuracy. The scheme is stable but not accurate for us for such a large time step. Now, to close the this particular concept, let us recap that we introduced the heat equation and the backward in time centered in space discretization, which gives us a tridiagonal system to solve at each time step. we provided we proved using the von Neumann analysis that BTCS scheme is unconditionally stable, meaning we can take arbitrarily larger time steps without the solution blowing up. However, we also noted that accuracy still limits the practical time step. With this foundation, we are ready to move on to more advanced topics in as followed. So in many fluid dynamics problems, we have not only diffusion but also convection, the transport of a quantity by a flow field. The simplest model is the one-dimensional convection diffusion equation as displayed over here, where C is a constant advection speed. This equation describes, for example, the temperature in a moving fluid or the concentration of a pollutant in a river. So if we apply the backward in time and centered in space philosophy to this equation, we discretize both the convective term and the diffusive term at the new time level, so we can get the final form as displayed. So this equation is actually a natural extension, but as we will see, it introduces new challenges. We can again perform the von Neumann analysis on this equation. For simplicity, let us consider the pure convection case first, which implies that alpha equals to 0. Then the BTCS discretization would become um, as displayed, and the final modulus of the amplification factor would be giving us the equation as 1 over under root 1 plus lambda c square sine square k delta of x. So this is always less than or equal to 1. So wait, so is it stable or not? Actually, the answer to this question is that for pure convection, the exact solution should have the modulus of amplification factor equals to 1, which means that the wave should neither grow nor decay. Here we get the modulus of amplification factor less than 1 for all non-zero lambda c and k. That means the scheme introduces artificial diffusion, which is unphysical. But worse, if we examine the phase speed, we find out that the numerical wave speed is not the correct physical speed. It depends upon the wave number, causing dispersion errors. And for certain ranges, the scheme can actually be unstable if the convective term is treated with centered differences in an implicit way. Let us be very precise. In fact, BTCS scheme for pure convection is unconditionally stable in the sense that the modulus of the amplification factor is always less than equal to 1 for all values of lambda c. But it's not a good scheme because it is highly diffusive and dispersive. In the presence of both the convection and diffusion, the stability condition becomes more complex. But generally, the scheme remains stable for all lambda and lambda c's. However, the centered space approximation for the convection can lead to unphysical oscillations when the grid Becklet number is very large. So this is a known issue. Central differencing for convection is only stable if the diffusion is strong enough to damp out the oscillations. Now, to overcome this, we often replace the centered difference for the convective term with an upwind scheme. Upwinding uses information from the direction of the flow. So for positive value of the c, we approximate the first derivative as displayed over here. So this is the first order accurate, and it produces and introduces the numerical diffusion, but it eliminates the oscillation effects. For problems where the physical diffusion is very small, the numerical diffusion can dominate. So we can need a compromise. A common approach here is to use the hybrid scheme, switch between the central and the upwind depending upon the local grid Becklet number. Another approach is to use the high order upwind scheme to like quick or TVD, often abbreviated as total variation diminishing schemes. which actually maintains the accuracy while avoiding the oscillations. In the context of the implicit time integration, these spatial discretizations can be combined with backward in time centered in space scheme, leading to a nonlinear system because the upwind selection may depend on the solution itself. So for the fluid flow simulations, it's rare to use pure BTCS scheme with central differencing for convection. Instead, we use implicit schemes for the diffusion part, which gives stability, and treat convection more with more sophisticated, often explicit or semi-implicit methods. A popular strategy is operator splitting. We split the equation into a diffusive part, which is solved implicitly with BTCS scheme, while a convective part, which is solved explicitly with a higher order scheme. So this allows us to take larger time steps for the stiff diffusive term while accurately capturing the convection. So while backward in time centered in space, BTCS itself scheme is a simple implicit scheme. Its extensions to convection diffusion require careful handling of the convective term to maintain accuracy and avoid the spurious oscillations. Now, moving on, and let us move to nonlinear problems, a classical model that combines the nonlinear convection and the diffusion in Burger's equation, as displayed over here. So hence, here the convection speed is the solution u itself. This equation exhibits shock formation and is a simplified version of the Navier-Stokes equations. If we apply the BTCS scheme to this Burger's equation, we discretize both terms at their new time level as displayed over here. And if we notice that the convective term now involves products of unknowns at the new time level, this makes the system nonlinear. We cannot simplify as we cannot simply solve a linear system. We need to use iterative methods at each time step. So there are two common ways to handle this nonlinearity. The first is Picard iteration, also known as the method of successive substitutions. In this approach, we guess a value of u at any grid point I and time level n plus 1, say the previous time steps value, and use that guess to evaluate the convective velocity in the nonlinear term. That makes the system linear in the unknowns at the new iteration. We then solve the linear system to get an improved guess and repeat until convergence. In essence, we are solving a sequence of linear backward in time centered in space like systems, each with a slightly different matrix because the convective velocity changes. Then the second approach is the Newton's method, which is more robust and converges quadratically. Here we treat the entire nonlinear equation as a function uh, of u raised to the power n plus 1 equals to 0, and iteratively solve j partial u equals to minus f, where j is the Jacobian matrix. For this Burger's equation under discussion, the Jacobian is also banded. It adds contributions from the linearized convection term. Newton's method typically converges in a few iterations, but each iteration requires solving a linear system that is still tridiagonal or nearly so. So in practice, for problems like Burger's equation, we can use the Picard iteration if the time step is small enough, but the Newton's method is preferred for robustness, especially when shocks are present. The cost per time step increases because we may need several linear solvers, but the unconditional stability allows us to take larger time steps than the explicit methods, potentially offsetting the cost. So this approach of treating the nonlinear terms in implicitly is at the heart of the modern CFD solvers for the full Navier-Stokes equations. We often use implicit schemes for the viscous terms and treat the convective terms explicitly. or with a combination. But fully implicit methods like the ones used in steady state solvers rely on neutron iteration. Now let us go beyond one dimension, consider the two-dimension heat equation as displayed over here, and applying the BTCS scheme over here, we discretize both the second derivatives at the new time level. The resulting equation at the grid point I comma j would form into this particular resulting equation as displayed. So this couples each unknown to its four neighbors in a structured grid. If we notice, the resulting matrix is no longer tridiagonal. If we order the unknowns in a natural way, row by row, the matrix becomes block tridiagonal. Each block is a tridiagonal matrix, and the off-block diagonals are diagonal matrices. It's sparse but much larger than the 1D case. For a 2D grid with n points in each direction, the matrix size is n square by n square. So direct solvers like Gaussian elimination would be prohibitively expensive, of the order of n raised to the power 6 operations. Instead, we use the iterative methods. One classic method is the alternating direction implicit, which is often abbreviated as ADI method. The idea is to split the 2D equation into the two 1D problems, one in the x direction and one in the y direction. At each time step, we first solve a set of tridiagonal systems for all rows implicit in x, explicit in y. Then solve a set of the tridiagonal systems for all columns implicit in y and explicit in x. So the alternating direction implicit method is a second order accurate in time and allows us to use large time steps while keeping the work per time step manageable. For more complex geometries or unstructured grids, we often use Krylov subspace methods like conjugate gradient for symmetric positive definite systems, or GMRES for journal systems. Now, these iterative methods require only matrix vector products, which can be computed efficiently without storing the full matrix. To accelerate the convergence, we use the preconditioners approximations of the matrix that are easy to invert. uh, Common choices include incomplete LU factorization, which is ILU, or multigrid methods. Now, multigrid is particularly powerful for elliptic problems like the ones arising from implicit diffusion. It exploits the fact that low frequency errors can be efficiently smoothed on the coarse grids, leading to convergence rates independent of the grid size. So in modern computational fluid dynamics, we often simulate unsteady flows using methods like unsteady Reynolds average Navier-Stokes, which is abbreviated as URANS, or large eddy simulation, which is abbreviated often as LES. So in these approaches, the governing equations are time dependent, and implicit time integration is often preferred because the physical timescales can be much larger than the numerical stability limits of explicit schemes. However, accuracy still demands that the time step be small enough to resolve the important unsteady phenomena. So while we use the implicit methods like BTCS, backward in time centered in space scheme, or its higher order variants, to allow larger time steps, we must ensure that those time steps are physically appropriate. The choice of a time stepping scheme is always a balance. Uh, Stability, accuracy, and computational cost. So BTCS gives us stability for free, but it may not be the most accurate in practice. For unsteady flows, we often use second order implicit schemes like Crank-Nicholson or 3-point backward differentiation formulas, which is often abbreviated as BDF2, to achieve better temporal accuracy while retaining the stability. Now let us summarize what we have covered up till now. BTCS, which is the backward in time centered in space scheme, is an implicit finite difference scheme where the spatial derivatives are evaluated at the new time level. For the linear diffusion equation, this leads to a tridiagonal system that can be solved efficiently with the Thomas algorithm. Von Neumann analysis proves that BTCS is unconditionally stable for diffusion. We extended it to the convection diffusion and saw that while the scheme remains stable, central differencing for convection can cause oscillations unless the grid Becklet number is small. We discussed the remedies like upwinding and operator splitting. For nonlinear problems like Burger's equation. We introduced the Picard and Newton iteration to handle the implicit nonlinear terms. In multiple dimensions, the system becomes sparse but not tridiagonal, requiring the iterative solvers like ADI, Krylov method, or multigrid. Now, let us talk about some common mistakes when implementing the backward in time centered in space scheme. The first pitfall is using the time step so large that the solution becomes stable but physically meaningless. For example, smearing out a shock or failing to capture a rapidly varying boundary condition. Always check that your time step is appropriate for the physical time scales of your problem. The second pitfall is mishandling the boundary conditions in the implicit system. When you modify the matrix to enforce Dirichlet type of the boundary conditions, it's very easy to actually forget to adjust the right hand side correctly. A simple debugging technique is to compare the numerical solution against an analytical solution for a simple case such as a sinusoidal initial condition with known exponential decay. The third type of the pitfall is assuming that the matrix is constant when it's not. For variable coefficients or nonlinear problems, you must rebuild the matrix or its preconditioner at each time step or each iteration. Overlooking this can lead to incorrect results. So, to close, I hope that you now have a solid understanding of the backward in time centered in space scheme, what it is, why it's stable, and how it can be extended to more complex equations. So BTCS is a workhorse that teaches you the essence of implicit methods. From here, you can explore the more advanced topics like Crank-Nicholson for the second order temporal accuracy, high resolution schemes for the convection like TVD and WENO, Vino, pressure velocity coupling for the incompressible flow, the simple and piezo algorithms, and parallel solvers using MPI or GPUs for large scale simulations. So thank you for your attention. I will now be open for the floor now open the floor for questions. Thank you for watching.